A lot of you make some noise if you're from Hong Kong. Oh wow, got a great Hong Kong crowd. Oh, hoi sem yo ho do Hong Kong yan lai ting yang ka say gui lo gong tian ma. Okay, try to learn that right. Actually, the best thing I've learned from Cantonese is when someone behind me says, am I saying it right? What tam dao? What kan bu dao? So for some short people, maybe you can let a couple short people stand in front of you. Always let the shorter people stand in front. It just makes them so happy when you understand the Cantonese and you say, yeah, please stand in front. I don't want you to have to hide though. Thank you. So, but I am very happy to be talking about my passion for a long time about planets and try to keep it short. So, I mean, I could talk about life in the universe when I come back, or other things about planets, but no, I'm going to talk about what I found. And you can ask about all of that stuff on the discussions. So what I'm starting out with is here, this is a real observation. Because the sort of work I do is kind of statistical, it's hard to show a real observation. And then because we don't see the planets directly, most of the planets, we only see a small number of planets directly, but all of the planets that I'm studying, we actually don't see any of them directly. We just see them make the star wobble. So we have to rely on a lot of paintings here to get an artist's conception. An artist's conceptions, they're really nice, except I have to point out, planets would not look like this if you were really looking at it above the disk. Planets are so tiny, they would just look like a little dot if you could see them at all. Actually, when you stand outside, get away from the city lights and go sometime. Actually, there are some places in Hong Kong, the Astronomy Society, you can go to an island. They take you to islands where you can see the Milky Way in places in Hong Kong. Can't see it here. But you know, when you see a planet, even Jupiter, it looks just like a bright star. If you're out in space, it doesn't look any different, so it would look like that. So this is just an artist's liberty showing the planet, showing these things banging wind, and even the comets wouldn't be all that visible. But that's okay. We can kind of imagine what it really is. Okay, so what I'm talking about is that when talking about planet formation, how do planets form? We often think that when we figure that when a planet forms, the planets probably clear a gap in the disk. The planets form in a disk around a star. And now it's amazing that there's observatories that are actually able to see planet-forming disks. But just like I was saying about the painting, the planets themselves are too small, but they still don't know if there's an actual planet hiding in this disk. But it's pretty suggestive that you have these gaps. But what I found has to do with, you notice there's a brighter area. Now part of the reason it's brighter could be just, it's closer to the star. But there's also more material. It has to do with what we call the snow line or the frost line. And just like where I grew up in Utah, you'll see a frost line on mountains. Well, when planets form, you actually form stuff coming out. So I was looking at the data planets and trying to understand, I was actually trying to understand the eccentricity. The eccentricity means how circular or elliptical, how oval a planet's orbit is. And I started noticing something, that there were fewer planets in a certain range. And so you can separate planets by the stars by a few things. And one of the most important things about stars, kind of like people, is the stars, they go from young to old. Except we tend to call stars, instead of calling them old and insult them, we call them evolved. Because when stars get evolved, they get bigger. they puff up. They actually get brighter. You might think at first the stars, as they use up their fuel, that they get dimmer, but no, it actually, having the dead fuel in the center causes the fuel to burn further out in the star. And so it actually makes for a bigger furnace, a bigger fuel burning area, so they start puffing up even more. Now, an important difference for planets is, I know that Sunshine and Morning Post said no jargon, but I've got to tell everybody about metallicity or heavy elements. And us astronomers, we're kind of strange. When we are strange. Yeah, I come from a strange place. One thing strange about us is that we call anything heavier than helium a metal.
Everything is heavier than helium.
Everything except for hydrogen in the universe. Yeah, hydrogen and helium are the lightest things, and everything else. So it's like we're all made out of metals, including the oxygen in this room, which is kind of stupid to call oxygen a metal. I guess we're a little stupid about that. But the point is that if you want to make a planet like the Earth, if you want to make a rocky planet, you got to have these sort of heavy elements, or what we call metals. You've got to collect stuff like iron and silicon and that sort of thing. And so that's why you got in our solar system, you've got the first 4 planets, Mercury, Venus, Earth, and Mars. We don't have to have much gas on Mercury, Venus, Earth, and Mars. And actually for a planet, the Earth does not have much gas. That's why global warming is so bad. Our atmosphere is tiny. Our atmosphere is weak and rollable, and we don't have a real solid atmosphere like Jupiter or Saturn. In fact, one thing you'll be able to remember this by is the Earth doesn't even have as much gas as Uranus. That's right. That's what makes. That's exactly why Uranus is more massive than the Earth. Uranus has more mass than the Earth. And Uranus is an important planet when talking about planets, because we got 4 giant planets that have a lot of gas. They have runaway gas. And we like talking about Jupiter. Okay, when we first discovered planets in 1995, we talked mostly about Jupiter, the most massive planet, because that's all we could find. Now, what I found about this gap, and I'm going to jump it down there, hopefully. Okay, these are all the planets.
All the gas talk.
Yes, it's all the gas talk, having a hard time. Yeah, so all these planets past 100 days. All of these planets, I'm telling you that here I found a gap. I found the gap in the distribution of gas giants. These are all, every planet that's found here is more massive than Uranus. It's not more massive than Jupiter anymore because we have found planets. Uranus is less massive than Jupiter. And so astronomers like talking about super Earths, and we're trying to get down below the mass of Uranus, but astronomers are wimps. They talk about trying to get down below the mass of Neptunes. They call them sub-Neptunes, but come on, Uranus is less massive than Neptune, so Uranus should be the boundary line. And I really do think it's because they want to not be laughed at that they call them sub-Neptunes and not sub-Uranuses. That with 3 syllables. But anyway, it actually, the least massive planet actually is close to the mass of Uranus. So that is the boundary here. Every planet above 100 days. Now, we found some super Earths down here. So what this is, this plot here, this is a plot of the counts of all the planets by the period or the year. So the Earth would be, the Earth would be here at 365 days. And what I was going to point out here is we have to use logarithmic plots, because here, where you don't have a logarithmic plot, all these rocky planets in our solar system, if you plot our solar system, you just get everything squeezed here too much. Now our solar system has the rocky planets close in, short periods, and then the gas giants outwards. But it turns out that that's not necessarily planned, a template for all the solar systems. So when I was looking at this, I found that if you take all the planets that are going around stars like our sun in terms of age, not too evolved, not too puffed up, not too hot, pretty kind of close in temperature and mass. If you do that cut, see here's the plot of all the planets around stars, including stars not like ours, and you'll see all the planets have this pile up, this many 100-day, 700,000-800,000 day pile up, and you'd expect that. You expect that from the snow line that I talked about, that when planets form, they do kind of pile up around where the frost happens, where the ice will see out too close to the star, the water just evaporates. The stuff that makes planets evaporates. And so it's a little harder to make planets here. Now, over here on the right-hand side, I've also taken all the sun-like stars, and I've separated out in red the planets. Okay, I made a mistake a moment ago. I call them stars. What I mean is planets of stars. We can only really measure these properties of the stars. But the planets of stars with a lot of elements in red here, they have this surprising gap. It's not one pileup. Now, even sun-like stars in blue that have less material, they even have kind of a normal pileup. There are a few here. So this is the main point of my discovery, and I know there's a lot of exciting things I can tell you that other people have discovered, but since I found this unusual thing, and I've had some people tell me, a Berkeley professor was like, I don't believe this is real, because it shouldn't be there. A lot of astronomers believe it's there, and so as far as it shouldn't be there, let me go here. If I've done some simulations, I've done two sort of simulations. One, I've done a random simulation. What if you take this line here and just extend it over? What's the chance, just by probability? And it's actually, the chance that you'd have a gap here, if you fill it in, is 1 in many tens of thousands. That's statistics. Even better is, what if you take these, and it turns out there's 33 planets here. There's 15 here and 14 here, and actually, okay, this is the width of the gap. The gap is actually cuts into here just a little bit. So there's 33 objects that are all outside of my selection of stars that are like the sun and have a lot of material. The chance that all 33 would be out of this selection is, I actually wrote out all the zeros, 30 zeros here. If you can't see it, it's not all that impressive, but yeah.
Thank you, John.
So it's just virtually impossible that this gap here, this width, is by random. And so I'm going to be publishing that, working on that. So about the painting here, so maybe these gaps here that are around all the stars, maybe there's actually a gap here around all the stars. If you look at the solar system, you know that we have a gap in planets, the asteroid belt, and this gap actually corresponds pretty much to the asteroid belt. Except, to be honest, that's why I talk about mass. This gap starts at 653 days. Mars would actually slightly be in the gap, but there probably are rocky small planets in this gap. So that's my own personal discovery. Of course, I'm interested in planets. We're interested in planets for many things. It's, in my opinion, extrasolar planets are the most sure way that we'll find life in space. We may find it in our solar system, but there's just not very many good places to look in our solar system. Our solar system, any place outside the Earth, is pretty bad. And this gap is actually kind of important because it tells you that there could be fewer places to look within this gap. I don't know whether the gap extends down to Earth planets, but it could affect the number of moons. So this also relates to, it was also my earlier finding, this is the orbital eccentricity by period of planets, and it turns out that the eccentricity of planets with more material is higher. I found that makes sense. That just, if you're playing pool and you hit the ball, if there's a lot more material, if there's a lot more balls, you're a lot more likely to hit another ball. And so planets with more material probably make more planets and make more balls to bang into each other and have orbits that are circular. Okay, so I think I pretty much told you my conclusion. If you want to ask about my discovery about the distribution of planets or life in the universe, I'm game to answer that or tell you stories or try to do a comedy joke or something.
Smarter than that.